So everyone, let's begin. I'm very pleased after an arduous day of sitting in LaGuardia that Duncan Watts has been able to join us from New York. I think truly in this room he's a man who does not need an introduction, but I'll just say a couple of words, which is actually I think the first time I introduced Duncan for a talk was probably 15, 17 years ago when you came. I don't know if you remember when you visited Lars Eric and myself at Harvard.
Oh yeah, I don't remember talking.
Yes. I remember a lovely dinner that we took you out to, but I think a particular signature of Duncan's work is well, they're a dual signature really. One is sort of looking at these really important questions, and I'd say social science, generally social science, or not exclusively social science questions, but bringing perspectives that I think were not in the social sciences when he began his career and now are, in significant part because of his work, but also just these really big picture interesting questions around, how do we solve problems together, and how, if we're trying to predict stuff from big data, what are the issues in making those predictions, and understanding, really working across the sociology and the data in a way that that was quite distinctive to, really quite distinctive to Duncan's work. And I think really pleased to have him here to comment on a topic that I have some I hold near and dear to my heart. So with that, again, very pleased that you could make it up here with success.
Great, thank you, David. It's nice to be back here. I think I was here about a year ago for your workshop on fake news, which has now become a raging storm of interest among the scientific and journalistic community. So it's nice to be back. So yes, as David said, I want to talk about computational social science, and my trajectory through social science has been a little bit unconventional. I started off really working in dynamical systems in sort of physics and engineering, and then became a sociologist. And so I've always had this particular view of what makes sociology, or really more generally social science, social, and that it's this problem that in sociology we call a micro-macro problem that everybody else refers to as emergence, where you have things happening at different scales. And so if you think about the kinds of problems that social scientists study, whether they're families or firms or political parties or markets or entire cultures, we talk of them as if they're things, as if they're actors, as if they have characteristics and maybe even preferences and take actions. But we understand at some level that this language is really a convenient fiction, that these social actors are not really actors. The real actors are actual people who have the beliefs and feelings and take actions, and that these real people are interacting with each other through networks in very complicated ways, and somehow the individual level behavior, the micro level behavior, is aggregating up to produce these macro level facts that we want to understand. So we've known this in social science for a very, very long time. Probably 100 years ago people started talking about this. But there's not, there sort of historically hasn't been too much we could do about it, because as everybody in this room knows, emergent networked phenomena are extremely difficult to study empirically. So just collecting observational data about large networks is extremely onerous, especially once you get up to millions or billions of individuals. But even at the level of thousands of individuals, you often have many different networks connecting them. They change over time. So it's extremely difficult to collect all of that data. And then if you want to do more than just describe what's going on, if you want to be able to connect causes and effects, you may have to do experiments, and that's even more difficult to do and actually quite often impossible in the social realm. So if you sort of think back to your high school lessons about the scientific method, where you develop your hypothesis and then you go test it, and having tested it, you find presumably that you're not quite right and you have to go around the loop over and over again. If you can't do that sort of second half of the scientific method of testing and rejecting theories against data, it's very difficult to make progress. And so I think it's fair to say that in the social sciences over the last 100 years, we've developed an extraordinary collection of interesting ideas and theories and hypotheses about what might be true in the world and why things might be happening, but we have a much less well-developed ability to discriminate among these different theories and to reject theories. So, what has been so exciting to me about the last decade or so is that you start to see these historical barriers lifting, and we're generating not just more data, but classes of data that are, at least in principle, and of course there's plenty of problems here that we can talk about, but at least in principle are matched to the theories that we've developed over the years. So in this talk I want to roughly differentiate between two classes of data. The first class, which is sort of generically referred to as big data, is data that is generated by processes, platforms, technologies for purposes other than doing social science. Right? So everything that you do in your daily lives, that using your phone or emailing or e-commerce or participating in social media, searching for things, browsing things, etc. All of this is, of course, generating enormous amounts of digital breadcrumbs that, in theory at least, could be repurposed for by social scientists after the fact to try to understand basic social processes. But the second type of data that I want to talk about is where we have used the web to design and run experiments of the sort that psychologists have been running in physical labs for probably about 80 years now, and economists for somewhat less time than that. But now in a virtual environment. And so, as I'll discuss, this has some interesting advantages. And so, people debate, I think, the meaning of computational social science is a somewhat contested term. It used to mean something else entirely. It used to mean agent-based models. And then David and his colleagues sort of just reappropriated that terminology back in 2009 and defined it to be the use of digital data. I have a somewhat ecumenical view of this. I think that all of these methods, everywhere where we're sort of seeing the intersection of computational methods with the social sciences, is as far as, and even computational thinking more broadly than just methods, I think it represents, to me, computational social science. So with that as background, I really just want to illustrate things by example, and just really even more restrictively than that, examples of research that I've worked on with my colleagues over the years to illustrate what I mean by these two different classes of data. I'll just make two further points. One is that even though the data is new, the questions are not. In fact, pretty much every question that I have ever worked on is an old question in the social sciences, sometimes decades old, sometimes centuries old. But by bringing these new types of data to bear on these old questions, we can, of course, generate interesting new insights. And the other point that I hope I can sort of broach as we go along is what we've been learning through these exercises of applying new kinds of research designs to these old questions is not just some of the advantages of digital data, but also some of the disadvantages, and these highlights and challenges that I think would be worth our time to focus on in coming years. So, moving right on, I want to talk about social contagion. And again, this is a topic that is familiar to many, if not all of you, and I would suggest that when we think about contagion, what we have in our mind's eye is something that looks like one of these pictures here. And I would say that for biological contagion, this is not a bad image. If you think about the outbreak of Ebola in West Africa a few years ago, it probably happened something like this, where a single person, like the red dot in the middle of this picture here, gets infected from an animal reservoir and then goes home and gets sick and infects a few of his family members or neighbors, and then each one of those in turn infects a few other people, and each one of those infects a few other people. And then over the course of time, you see this multi-generational branching network where a large number of people get infected in total, but in each branch, only a small number of people are getting infected. So this is a very sort of common metaphor, and in fact it's more than a metaphor, it's often enshrined in the very mathematical models that we use to describe contagious processes. So we tend to import this when we talk about social contagion, or things going viral online, social epidemics and so on. Something like this mental model gets transported over, and again, this is true of the mathematical models as well as the sort of rhetoric around these problems. But going back to the data, historically the problem that we've had in studies of adoption and other applications where it is posited that contagion is at work, the data that we have does not look like the picture that I just showed you. In fact, it looks more like this, where on the x-axis you have time, and on the y-axis you have a cumulative aggregate count of, in this case, adoptions. So on the left-hand side, we have a figure, the main figure from a very famous paper by Coleman, Katz, and Menzel, where they were studying the diffusion, or so they claimed, of tetracycline among doctors in the Midwest. And on the right-hand side is a figure from Everett Rogers, textbook Diffusion of Innovation, which might be the most cited book in all of social science. So these are very sort of core representative figures of how people have thought about social diffusion. And the claim that you get from these figures is they have this sort of characteristic S-shaped curve, more characteristic in Rogers' stylized version of it than in the actual data. But if you sort of squint at that, you can imagine that it represents an S-shaped curve. The idea is that you have some, just like in the picture I showed you, some small number, possibly just one initial adopter who's infecting a few people at a time. And so you have this slow takeoff, and then once the thing gets rolling, you see an exponential growth in adoptions, and then eventually the population of susceptible individuals is exhausted, and you see this asymptote, hence the S-shaped curve. So, there's some problems with S-shaped curves as evidence for contagion. The first, which has been pointed out a number of times, is that lots of things generate S-shaped curves. Lots of different, substantively different contagious processes generate S-shaped curves. But more than that, even processes that have no contagion associated with them all can also generate S-shaped curves. So just assuming some heterogeneity of propensity to adopt over the population, you can get something that looks like an S-shaped curve. And once you introduce marketing efforts, and most social processes at some point or another have some sort of marketing or media influence, you can get pretty much any shaped curve that you want, including an S-shaped curve. So that's one problem. The other problem is a little more subtle, only a little more subtle, but it's that when we study things in the social sciences, as in many other areas, we tend to only study interesting things, right? I mean, why would you study uninteresting things? But most things are uninteresting. Most attempts at diffusion don't diffuse. Most books don't sell very well. Most people are not successful. And so if you want to learn about what causes something, what differentiates not success from success, you have to study both of them. But if you're only able to collect data on the things that spread or diffuse far enough that you know about them, then you're effectively censoring on the variable that you're selecting on the variable that you're trying to explain. So this is a very sort of obvious, trivial problem in statistics, but it nevertheless confounds many conclusions that we draw about these sorts of processes. So if we want to really understand, what is causing diffusion, or whether or not we are even seeing diffusion, we have to have data that satisfies two properties. One is that it is observable at the individual level, that we're seeing the actual person-to-person transmission events. And we have to sort of have something like a total census of everything that's trying to diffuse. Right? We want to be able to say, what's the difference between success and not success? So naturally, I'm going to argue that the web helps, at least somewhat, with these problems. And going back just over a decade now, we have started to see a number of papers now, a very large number of papers that use data, digital data, web data of this sort. And so now we can ask new questions. Like, for example, when we see diffusion, how much of it is viral? What do we even mean by viral? I mean, this is we sort of use this word so frequently that of course we know what it means, but maybe not. And then finally, well, I guess I'm not going to answer that question today about how predictable it is. But that's definitely a question that one could ask, and that we have done some work. So I'm going to just talk about a couple of papers. The first one was done with Sshaped now at Stanford, and Dan Goldstein, who is now a colleague of mine at Microsoft Research, back when we were all at Yahoo. And we were interested in this question of how much spread is really viral. And the way that we went about it was to gather data from a bunch of other projects that we had worked on, or that our colleagues at Yahoo had worked on, that were designed to answer different questions. But they all had the property that the design of these studies had a kind of social referral component to it. So all of these projects were in some sense designed to go viral. And so I'm not going to go into detail about these different projects, but one of them was a Facebook app that we built, back when people were building Facebook apps. We did not sell our data to anybody. Although, actually, it was all about political beliefs and how similar you are to your friends. So this could have been really valuable stuff. It never occurred to us to tell to anybody. Also, we promised not to, which seems like that. That's another topic. But it was about we were trying to measure how similar you were to your friends in terms of your political beliefs, and how similar you thought you were. So the difference between real and perceived similarity. So a completely unrelated question, but because it was a network survey, it had this sort of gamified social referral mechanism built into it, where we'd ask you a question about your friend, and then if they hadn't answered it, we would encourage you to encourage your friend to also use the app. And of course, we hoped that this thing would spread wildly and get millions of people participating. It was not quite that successful, but it did spread somewhat. Another example was a video viewing, synchronous video viewing app that our colleagues built, where people could watch videos together, and I could pause the video and yours would pause as well, and then we could chat and so on. So it had a sort of a network mechanism built into it. We had data on a premium IM service that Yahoo had launched. We had data we had a sort of early dump of Twitter data. So you can see these are pretty varied data sets, and that was really the point, because each one of them, you could complain, and people did complain, that they were very biased. Right? They were very unrepresentative. Facebook back in 2010 was, didn't have 2 billion people. It was a fairly sort of self-selected, liberal skewing population of people. And so you could say, well, Facebook's kind of weird, whatever you want about the world from Facebook doesn't really apply, or you could say the same thing about Twitter. You could say the same thing about people who watch videos online. So our point in this design was that each one of these domains, as we called them, had certain biases associated with them, but they had different biases associated with them. They were different populations, they were very different in magnitude, they had different adoption mechanics, they had different networks associated with them. So they were different in very many ways, and so if we saw similar patterns across domains, we felt confident that those patterns would be fairly robust. And in fact, we saw remarkably similar patterns across all of them. So there's a lot on this figure here, so just look at the top right-hand corner for the moment. So this is Twitter. What these little motifs mean is that we start with the dot. That means that you introduced a shortened URL. So back then it was bit.ly URL, now it would be a t.co URL. A piece of content from somewhere on the web into Twitter, and 93% of the time nothing happened, right? So if that is your experience of Twitter, where you're shouting into the void and no one is paying attention to you, then you're in excellent company. That happens to everybody. About 5% of the time, one of your friends retweets it. About 0.9% of the time, 2 of your friends or followers retweet it. 0.3% of the time, 3 retweets. And then 0.3% of the time, 1 of your followers retweets it, and then 1 of their followers, who's not one of your followers, retweets it. So that's starting to seem a little bit viral. But you'll notice that between those 5 motifs, as we call them, that's about 99 and a bit % of everything that we observed. So of all the things that were introduced into Twitter, and there's about 40 million URLs, over 99% of them look like one of those 5 things. Okay? So not very viral. Now, if you then look across the remaining 5 domains, we see very similar patterns. In fact, there are 5 most frequent motifs associated with each of 6 domains. So there are 30 possible structures that we could have seen, and we only see 7, which is those 5 plus this one here, where there's 4 retweets, and this one over here, where you have 2 retweets from your followers, and 1 of them gets an additional retweet. So very strong consistency across these very, very different domains. And even the numbers were sufficiently, the frequencies were sufficiently similar that we were inclined to aggregate things even further and lump everything together and conclude that about 90% of the time when something is introduced into a population, nothing happens. 8% of the time there is 1 additional adoption. 1% of the time there's 2 additional adoptions, and 1% of the time is everything else. So the conclusion here is that everything that you've ever heard of, every interesting viral video of cats or Korean pop singers is in that small blue bar on the right-hand side. And if you know about scale-free things, you might say, okay, that's interesting, but we know that in real distributions, including distributions of storms or avalanches or forest fires, that the things, and human epidemics, that even very rare events can be sufficiently large that we care about them, right? So going back to human epidemics, 100 years ago roughly was the Spanish flu was happening. About 1 billion people in the world were infected in this one event, about a third of the Earth's population at the time. So even if that, that were in our little blue bar on the right-hand side, you might say, well, the event is rare, but the number, it accounts for a large fraction of the total number of people who got infected. So So if you count all the people who got the flu over the course of human history, I would wager that more than 1% of them were infected in that single event. Okay? So in this case, we can really rule that out. So there are no Spanish flu epidemics in this data. So that's what the second line says. It's not just that 99% of events are small, but 99% of adoptions are less than one hop from the node. Right? So if your intuitive or heuristic definition of viral is things that spread from multiple steps, then fewer than 1% of adoptions in this data is viral. Okay. But still, we know these things happen, right? Don't we? This is, of course, Gangnam Style. It's a little bit out of date. Maybe I need the, what was the song last summer? Last something or other. That was, that finally broke the record that Gangnam Style had set for most downloads of video on YouTube. This was when Google had that. What's that?
What broke the record?
This, well, this.
Yes.
Oh, there was some song last summer. Some, you know. There we go. See.
Oh, that one.
Yeah. But you know, this is where Google had to add an extra digit to their counter because it broke the clock. So, you know, surely, you know, this is viral, right? I mean, certainly is referred to it as viral. But what we really know, all we really know about Gangnam Style and other similar events is that they're really popular, right? And they sort of got popular quickly. So there's something about time there, there's something about the, you know, height of the y-axis. But, you know, the Super Bowl is also really popular, right? About 100 million people watch the Super Bowl every year. But you wouldn't call it a viral event, right? You would call it a broadcast event, right? And so there's no, you can't conclude just from the sheer popularity of something that it was viral. And in fact, we know that Gangnam Style was heavily covered by all of the mainstream media at the time. You know, it was on the front page of Yahoo, which at the time had about 100 million daily visitors. So, you know, a good chunk of that, you know, billion plus views could have come from, you know, Yahoo, MSN, you know, being on Today Show, etc. So it could very well have been a broadcast phenomenon. We can't really tell just from the data that we have. So this was the question that motivated the second project. In addition to another question that we had received in response to the first project, where some of our colleagues had said, well, you know, that's interesting, but all this really means is that your data is kind of boring, right? That you didn't get anything interesting in your data. So if you study a bunch of stuff that's like not interesting, no surprise that there's nothing viral in it. So it's a little hard to deal with that critique conclusively, but one thing you can do is just go get a lot more data, and so that's what we did. And this is now, again with Sharad, but Jake Hoffman and Ashton Anderson, colleagues at Microsoft. And so at that point we were at MSR and we had the whole Twitter fire hose, so we just got everything on Twitter for an entire year. Every video, every news story, every image, every petition posted to Twitter in the form of a shortened URL over 12 months. So this is now over 1 billion observations, so a couple of orders of magnitude more than we had before. And then to deal with this criticism that we were mostly looking at uninteresting things, we further restricted to just the events that got at least, just the pieces of content that got at least 100 retweets. 100 retweets is a lot, right? You know, I may have gotten 100 retweets, you know, once ever, you know, in my sort of Twitter career. But that's already 1 in 3,000 events, so it's way rarer than anything I showed you on the previous slide. But because we have over 1 billion things to start with, we have 350,000 of these rare events, and so now we can study them. And what we're going to do is study this property that we defined called structural virality. Now, to understand what this is, forget what you know about virality, because it's not the parameter, it's not the beta parameter in your model. This is, you imagine that somebody introduces a piece of content, it gets a bunch of retweets, it spreads through the network, at some point it's done. Imagine that along the way it's kind of lit up the pathways that it has passed along, right? So now you have some structure, right? This sort of vestigial structure that's being left behind by the diffusion process. So you can treat it as a network, and you can just measure things. And what we're going to measure is a very simple thing, just the average pairwise shortest path, right? There's a bunch of other things that you could define that turn out to be roughly similar, but this one we thought is easy to explain. And so if the diffusion process is a broadcast, then this number is very close to 2, right? Because every pair is 2 steps apart except for the broadcast node. So as n becomes large, this will asymptotically approach 2. At the other extreme, we have something that we kind of think of as a viral process where you have many generations and only a few branches at each generation. Then it's going to be a tree that has a depth proportional to log n, and so the average shortest path length will also have a depth will be proportional to log n. So you get a number for each one of these 350,000 cascades. It's somewhere between 2 roughly and log of n.
And then?
Hmm?
And then?
And then? N, yes.
The longest one.
Oh, yes, of course it could, yeah, right. But it's possible that you can have it's theoretically possible you could have just a chain. But empirically, we did actually find something that was pretty close to that. But that's, right, that's not 1 in a million, that's like closer to 1 in a billion. Right, so for everything else, between 2 and log of n. And so now we can ask, what is the distribution of this number, right, over these events? In particular, how much diversity do we expect to see? So you can ask yourself, for popular events, for things that are popular, are they mostly broadcast, or are they mostly viral, or are they some combination of the two? And then you can also ask, as they get increasingly popular, does this relationship change? Do you see things get more viral or more broadcasty as things get bigger? So to answer the first question, we just took a sample of events that were all about the same size. And then we binned them according to their structural virality, and then we just looked at some of these examples. And so you can see, and this is just a very simple point here, that there is tremendous diversity of structure, right? So starting at the top left, the black triangle corresponds to a broadcast. So this is a CNN story. CNN has lots of followers. A bunch of them retweeted it. It just looks like a black triangle because all the lines are plotted on top of each other. And then there's a little trickle of additional retweets, but most of the action is in that initial broadcast. And then as you go from left to right and top to bottom, things get increasingly more viral in this structural sense. And so if you go down to the bottom right here, this is a New York Times obituary about a little-known French freedom fighter from World War II, who was sort of a real-life version of the world's most interesting man. It was a fascinating obituary, but nobody had heard of this guy, so he was not a famous person, and so it spread in a very different type of way. So point number one, tremendous diversity. All of these things are about the same size. They all have about the same popularity, and yet clearly that number is masking very, very different types of structure about how things are spreading under the hood. The second thing to note is these little inserts underneath show you sort of the old type of data, which is just number of retweets over time. And you can see that that's pretty uninformative, right? That it's there's no obvious correspondence between the structure and the time series. In fact, they all look about the same, except for this odd one in the middle down here. Okay, so the second point, how does this pattern change as we go from merely popular to very popular. And so this is now breaking things down by type of media very coarsely. And the box plots show you everything, the bins by popularity or size, the black lines are the median, the boxes are the interquartile range, and the dots show you the full extent of the data. And so you can see from these extended lines, the point from the previous slide, that there is a lot of diversity. But the dominant picture is that everything is pretty broadcasted. In particular, for pictures and videos, the median structural virality is less than 2 for pictures, less than 3 for pictures, just above 3 for videos, and there's essentially 0 correlation between size and structure, right? So what this means is that the size of the overall cascade is mostly determined by the size of the largest broadcast in the cascade. So this is what we used to call the Justin Bieber effect, because at the time he was the most followed person on Twitter. I think it's now been rechristened the Katy Perry effect or whatever. She has 100 million followers. So these celebrities, and they're mostly celebrities, have astonishingly large followings. That 100 million is sort of Super Bowl numbers. And so really what we're seeing is, it's always a little tricky to talk about critical versus subcritical and scale-free networks because it doesn't really exist. But intuitively, this is a subcritical process in the sense that it's dying out continuously. But then it occasionally hits one of these enormous hubs that give it a burst of life and account for most of the retweets. So that's mostly what we see for pictures and videos, and I think it's probably fair to say that celebrities mostly tweet pictures and videos. They're not super engaged in news, so you don't see so much of that. You see a somewhat less of that effect for news and a somewhat higher correlation, although it's still very low. And then petitions, again, are essentially no correlation between size and structural virality, but curiously, and for reasons that we really don't understand, are just on average more structurally viral than these other types of content. Okay, so what can we learn from this? Interestingly, you can get a lot of these features just from a fairly sort of simple SIR type model. And so it's not that the models are wrong or that they're not applicable to processes like this. It's just that we've sort of been studying them in the wrong regime. So a lot of emphasis in the theoretical literature has to do with the epidemic threshold. So what is the point at which things go from not spreading to spreading? And if you're an epidemiologist, you want to keep things below the epidemic threshold, and if you're a marketer, you want to get them above the epidemic threshold. But the concern is what are the conditions on the network, on the infection parameter, on the refractory period, whatever parameters you're putting in your model that govern whether things are sub or super critical. And what we're seeing here is that everything is well below that threshold, right? And so if we're going to study these kinds of processes, we need to look at these processes that have very, very low traditional virality. So most things don't spread, and most things that do spread spread in not because they're growing exponentially, but because they're encountering one of these hubs. And I don't see Alex in the audience, but this, to us, was very reminiscent of a paper that you wrote with Romualdo Pastor-Saturas way back in 2002 or something about worms or computer viruses that had a similar kind of property where they were operating in this subcritical regime, but because they were being forwarded by people's email contact lists, some people had very large contact lists, and they were sustaining these viruses for much longer than you would have suspected at these subcritical rates. So, this poses some interesting questions for how to model social contagion, and I think also should be of interest to people who are approaching it from a practical perspective, where you have to think about seeding strategies that don't depend on individual people being able to make things go viral, which is an idea that has been popular for about 20 years now. And then finally, I would add that, even though it's probably true that people have used the phrase big data a little too often, there are certainly cases where the bigness of the data really helps, and I think this is one of them, namely where you have rare events, and you need potentially a billion observations to ask the kinds of questions that we asked. Okay, so I want to move on to talk about virtual labs, and again, this is a topic with a long history, and I think psychologists have been doing physical lab experiments since about the 1930s, and sociologists got into it in the 1960s, where they studied organizations in the lab, and they would have elaborate setups like the ones shown in these pictures. And there are certainly some important advantages for studying things in the lab. First, there are certain questions that you can only really address if you are, if you have the ability to design the data collection process from the question that you're answering. And all the Twitter data in the world will not tell you how groups of people collaborate to solve problems. Right? So when we look at Twitter, we're very kind of restricted by the data that Twitter has chosen to collect and the design of the platform and what people use it for. In a lab experiment, we have a lot more freedom to come up with questions that are interesting to us. We also have a lot of procedural control, right? So we can randomly assign people to treatments. We can do much better about causal inference. So there are, in terms of asking why type questions, the lab experiments have some really fundamental advantages, but they also have some very important limitations, and many people have pointed these out before. You can only trap undergraduate students in a lab for so many hours before it becomes unethical. You can only trap so many of them in a lab before it becomes physically untenable. So there's really sort of strict limits to time scale and sample size. Also, it's extremely difficult to design complicated interactions. Right? So we tend to study very simple tasks, very simple interactions. And finally, we are often doing these experiments in university settings, and so the inferences that we can draw are often restricted to the pool of undergraduate students, often at large Midwestern universities. And so this acronym WEIRD stands for Western Educated Industrial something democracies. So very just whatever. The point is that it's a very narrow, unrepresentative sample of the world's population. And so these are clearly reasons for concern. In particular, and what got me thinking about this is that they can be fine for testing specific theories. If you have some sort of theory of cognitive dissonance or theory of social loafing or some particular theory that you want to test, you may very well be able to design an experiment to test that theory. What they're not so good for is external validity. So if you want to take that conclusion and say, what does this mean for organizations or communities or politics, it becomes much more difficult to answer that question. And they're very expensive and they're really slow. So, here's the vision. We would like to use the web to create virtual labs that relax some of these constraints. So if you think about, very heuristically, the design space of experiments, and we just collapse them onto these three rough dimensions of how long they go for, how many people are in them, and how realistic they are. Almost all the experiments that we do in physical labs are sort of collapsed down there near the origin, and the real world is kind of out here, right? Lots of people doing complicated things for long periods of time. So what would be nice is if we could sort of push this red dotted line out somewhat into space. So I'll just very quickly summarize a few experiments that we have worked on over the years that just illustrate how we can move out along each one of those dimensions on its own, but not all three. So this is a very old experiment done with Matt's Organic and Peter Dodds back at Columbia. We were interested in the substantive question of how social influence affects the dynamics of cultural markets. In particular, how to explain why hits are so much more successful than average and also so difficult to predict. And so we built a web-based experiment where we recruited thousands of teenagers online, and we sent them to this website, and they listened to songs by bands they had never heard of, and some of them only saw the names of the songs and the bands, and others saw a little number on the right-hand side of those tiles that told them how many times that song had been downloaded by people before them. And so there was a weak social influence signal that we exposed them to. And what we were able to show by randomly assigning people to different conditions is that social influence increased inequality. So popular things became more popular and unpopular songs became less popular. But it also became increasingly difficult to predict which song would become the most popular. So the scientific question here was about the construction of preferences in markets. But the sort of ancillary lesson that we learned that has also stuck with us is that we were able to get, actually we did a bunch of other experiments, and in total we had almost 30,000 people that we recruited for free to do social science for us. So this was a sort of profound discovery for those of us involved, we wouldn't actually have been able to. It wasn't just that we were able to shrink our error bars, right, by having a larger n, right? That would be sort of the easy thing to do. The point here was that, in order to test this hypothesis, we had to create entire markets, and each one of these markets had hundreds of people in it, and then we had to have lots of them in order to make comparisons between them. So then you need thousands of people. And then you want to try different experimental conditions, and so now you need tens of thousands of people. So the nature of the question required this sort of scale. So there's certain kinds of questions that you can ask at this scale that you just couldn't even ask in a traditional physical lab. So that's sort of, I think, the more interesting, if we go back to this sort of initial slide that I showed you about emergent processes and the micro-macro problem. If we want to do macro sociology experimentally, we have to have very large numbers of people. That said, it wasn't a particularly realistic experiment. It was a little bit like, music websites of the time, and so it had some external validity, but there were lots of problems with it. And there have been lots of problems with most of the experiments that we have conducted online of that sort. And so we've been sort of struggling with this question of how to find a problem that is studyable in a lab, sufficiently sort of simple that you can recruit a bunch of online workers from Amazon Mechanical Turk or wherever, and have them do it in a feasible amount of time. but is also sort of similar to what people do in the real world, right? And so we found an example that we called it, that's called crisis mapping. So this is the first crisis map that was ever made by Patrick Meyer back in 2010. And what it shows you is Port-au-Prince in Haiti in the aftermath of the earthquake there. And Patrick had this amazing insight at the time. So what happens when these disasters strike is the UN comes in, the Office of Coordinating Humanitarian Affairs, or UN OCHA, comes in and starts trying to coordinate all the relief agencies that descend on the area. And the problem they had in Haiti was that the devastation had been so extensive that the infrastructure was completely destroyed and nobody knew anything. Nobody had any information about where the problems were. And what Patrick realized is this sort of, in the age of cell phones, that there was a lot of information about what was happening on the ground, but it wasn't digestible by the UN. There's noisy, unstructured data that was coming up in the form of tweets and social media posts. And so he sort of assembled a bunch of volunteers, and they sifted through all of this data and they created this map. And the UN apparently found it sufficiently useful that they have requested maps in subsequent crises, and now there's a whole community of crisis mappers around the world. So when I was talking with Patrick about this, it was shortly after another crisis had happened. There was a typhoon that barreled through the Philippines in 2012, and he gave us all of the data, about 1,500 tweets from people in the Philippines who were tweeting about this Typhoon Pablo. And so Andrew Mao, who was a postdoc with us at Microsoft, built this incredible piece of software where we were able to recruit a bunch of people on Mechanical Turk and have them do crisis mapping in a lab. And so this is the real data from Pablo, scrolling down on the left-hand side. And these 16 Turkers have been given the task of sifting through it and figuring out which ones have useful information in them, and then cataloging them in this little collaborative spreadsheet here, where they're giving them different types of classifications. And then they have to geolocate them, which is not easy because they're not geotagged. So they have to do some sleuthing to figure out where these things are happening. And then they appear on this map, and they're also talking to each other, trying to figure out how to do this. And so we just gave them some basic training and instructions on what they were supposed to do. We didn't really tell them how to do it, so that was something they had to figure out among themselves. And so in the course of 1 hour, they were in fact able to produce a crisis map. And it was remarkably similar to the one that the Standby Task Force produced over the course of 24 hours in December 2012. So there's some external validity there. But what we were interested in actually was, how many Turkish should you recruit for this job, and what difference does it make? And this sort of taps into a larger, longer literature about the relationship between group size and performance. And we were able to recover some, so we actually recruited about 30 different teams of people of size from a single person up to 30 odd people. 48 different teams. And so some of them were quite large, and others were very small. And we were able to measure things like how much effort they were putting in individually and how much they collaborated with each other. And so you can see, roughly speaking, that as you have more people in your team, people put in less effort, which is consistent with ideas about free riding and social loafing. But they also benefit from being able to collaborate with each other. And we were able to show that, in fact, the benefit of collaboration at a sufficiently large group size outweighed the benefit of, outweighed the cost of free riding. And so these largest teams on the right-hand side were comparable with the performance of the actual real-world group. So finally, as I'm running out of time, and so now we're going to go back from being realistic to being unrealistic again and study the prisoner's dilemma, which I'm sure you know is like one of the most studied models in psychology and economics and sociology about how people cooperate. And more specifically, we're going to study a finitely repeated game of prisoner's dilemma. So everybody is familiar with prisoner's dilemma, right? Good to cooperate, rational to defect, bad when both people defect. And so, the theory, of course, says that everyone should defect the whole time. Almost universally in practice, what you see is something like this, where people know they're going to play 10 rounds against their partner. They start off cooperating, and then as the end of the game approaches, one of them tries to take advantage of the other one. The other one then retaliates, and they descend into mutual defection until the end of the game. So this is completely standard and has been shown many, many times. The question that we were asking is, what if you do it again, right? And then again, and then again, and then again, and you just keep doing it over and over again. What happens? Does this person who got defected on first, like this guy, does he sort of get a little bit disenchanted by the fact that, the other guy kind of took advantage of him? In the next game, does he defect on round 8, right? And if that person was going to cooperate, maybe that person becomes disenchanted, and so then they start defecting. You can imagine that, if people keep doing this with each other over and over again, that a few bad apples will eventually drive everybody back to mutual defection from the beginning. So that actually is the theory, right? That's what's supposed to happen. But it's very difficult to show it in a lab. And the reason is you can't run the experiment for long. So the most comprehensive study that had been done prior to ours, sort of tried to do this. They really outlined this as the question they were interested in. They surveyed the literature exhaustively. They ran a very careful experiment. And at the end, they sort of threw up their hands and said, well, we just couldn't run it for long, right? Because this unraveling process, it looks like it's happening, but it's really slow. So we just did it for longer. Except, let me just show you what it looks like, right? So this is Andrew's DS3 skills here. So this is one game, right? So we had actually had 100 people, so 50 pairs playing a game of 10 rounds each. And then we randomly reassign them to play someone else, and then they play a bunch of games. And that's what one session looks like, right? So 50 pairs playing 20 games with random reassignment each time. So that's about the length of Embry et al.'s study, and about the length of the longest studies that have been done previously. And so we just did that 20 times over the course of a month. Every weekday, the same people, mind you, right? So this is sort of a new thing that we were able to coerce Mechanical Turk into doing, is to you started off with 113 people, and we tried very hard to explain to them that we wanted them to sort of come back every single day at the same time and do this for a month. And we would, we sort of got them to commit to doing it, and then we reminded them every day. So commitment is useful, nagging is useful, and then finally we had some monetary incentive to stick around for the whole time. So about 98 of the 113 did in fact stick around for the whole time. So what did we find after that effort? Well, what we found was, again, for the first couple of days, completely consistent with everything that had gone on before. And you can see that in rounds 9 and 10, sure enough, people are cooperating at lower rates. So there's unraveling occurring. What's interesting is that after about 7 days, the unraveling stops. And it just kind of flattens out for the rest of the experiment. And this, I'm being completely honest with you, is not what we were expecting. We had very strong prior that everything would unravel by halfway through the experiment, and we had all kinds of plans for what we were going to do then, and they just kept at that level for right through the rest of the 20 days. So why did they do this? Well, so we looked at the individual level player strategies, and we found that about 60% of them were doing what the theory suggested they should do, which is start off being pretty cooperative, and then over time, they start defecting earlier and earlier as the game goes on. So T9 means I will defect on the 9th round, whatever you're doing. T8 means I will defect on the 8th round, no matter what you're doing. And so you see that some of these people are going all the way back down to sort of, in T1 is where I defect all the time. And there was one clown who actually did that. And everybody hated this person by the end of the experiment. It's a really bad strategy, by the way. Don't do it. Bad for you, especially. But interestingly, about 40% of people didn't do this. They just sort of didn't learn, right? They started off playing a conditional cooperator strategy, where as long as the other person cooperated, they will keep cooperating. And then people would defect on them, and they would just go back to being conditional cooperator. And so we called them resilient cooperators, and we were really, they were interesting because, we asked everybody questions about why they played what they played, and they had a variety of interesting explanations for why they were doing what they're doing. But the key thing is that they didn't just raise the average level of cooperation themselves, they stopped the unravelers from unraveling, right? That the unravelers sort of got to a point where they were balancing between, they knew they had to figure out that there were certain people in the world who were cooperative, and if they met one of them, it was in their interest to cooperate. And if they met somebody like themselves, it was in their interest to defect first. And so with a very simple model, we're able to show that right around the value that we observed empirically, it was pretty rational to stop unraveling. And so these resilient cooperators, and there's no reputation here, like there's no reward, there's no punishment, right? This is just purely people playing the game over and over again. We're able to keep the average payoff pretty steady over time, even though they were paying a penalty for it, right? So these vis-a-vis the people who were exploiting them, the conditional cooperators, the resilient cooperators, were paying a cost. Okay, so I have some sort of thoughts about things that we could do in the future, but I've already used up all of your time, so I'll just say thank you very much, and if there's time, I can take some questions. Do we have time for any questions? Yeah.
Well, I assume we should take at least 5 minutes for the questions.
I have a very long question.
Okay.
I want to ask you about computational stats and its relation to computational sciences.
Computational
Statistics.
So,
like in the example of social contagion and big data, so you talk about where you can see if the model works in that context. And I want to ask you to clarify, what do you mean? Like, how do we know if the model works? So my understanding of your approach is that we use prediction and machine learning. So we have training data set, holdout of observations, and then we see how the model works on the holdout. But in computational stats, we do inference plus machine learning. So I wonder, what do you think of that? Is that the better way to go?
I am not an expert either in statistics or in machine learning, so I'm probably the wrong person to ask. I have a fairly simple-minded view of these sorts of things. When people are making claims about prediction, my response is, compared to what, right? If you say, there are innumerable papers written by very competent machine learning people who make, claims of the sort, our, model performs excellently. And I think, what does that mean? I can predict the weather in Santa Fe, New Mexico with 80% accuracy. Is that good? It sounds good, right? But it's sunny 300 days a year in Santa Fe, New Mexico. So just by predicting it will be sunny today, every day, I will get 80% accuracy. So, so we've been trying to, advocate for a very simple, obvious thing, which is that everything is only good or bad compared to something else. And then when you look carefully, and of course it gets more complicated because there are lots of things you could be measuring? You know, do you binarize your data and use a classifier, or and do you have a balanced classifier and a unbalanced classifier? Or are you measuring R squared, or or root mean squared error? I mean, there's lots of different choices that you can make in your research design, and we showed actually in a recent paper that with exactly the same model and exactly the same data set, you can get very different answers depending on how you, which particular set of choices you make in your research design. So, it's very difficult actually to make any conclusions about whether prediction is getting better over time, right? Are we doing better at predicting cascades in Twitter using a billion observations with some fancy random forest model than we did with a simple linear regression model with one feature on 1% of that data? You kind of can tell, right? So that's sort of the level that we're operating at, right? Which is just sort of, let's try to be clear. And in terms of evaluating models, I think it's similarly simple, right? That we're not doing anything very careful about estimating maximum likelihood. What model is most likely to have explained the data that we're observing. We're not doing anything like that. We're just sort of making very kind of broad brush conclusions that, like, well, nothing is going viral, right? So whatever, if your model is predicting that, then there's a problem with your model, right? There's a lot of work in influence maximization where the assumption is that each seed is infecting thousands of other people, and we just never see them. Yes, sorry, there was Tina, and then behind Tina.
Thank you, Dr. Excellent talk. I had a question about the second part of your talk, the
Yeah.
virtual labs. I thought I heard you say that I can't have scale, time, and realism all at the same time. Is that right?
No, you just heard me say that we have not been able to do that all
I
at
see.
the same time.
I
Yes.
see. Have you tried?
Nope, not yet. No,
Why
it's
not?
difficult.
So
Just
no,
failure
because
of
there could be cases
imagination.
where you don't need all three. So is it the case that I don't need all three, or are there
Oh, I
cases
see.
in which you wanted all three, but it's just very difficult to set it up?
I think that we would like to be able to do all three. Yes. Like, let's imagine we wanted to study, diffusion on a large network over, months, right? We wanted, 1 million people in our network, and we wanted to, vary all kinds of things about the adoption process, and we wanted to sort of, have this, happen in real time over a long period. I would like to run that experiment, right? It just, it's difficult to do. So that's mainly just sort of a combination of logistical difficulties and some, some technical difficulties as well. Like, for example, you pretty much have to, with Amazon's terms of use, at least maybe this is somewhat out of date now, but when we were doing the corporation experiment, people had to go through a browser, right? So you couldn't, have an app on your phone that you could use. You had to interact with each other through a browser, and so there's just sort of, again, because they didn't design their system to do the kinds of experiments that we want to do. We can sort of run into all kinds of problems with the way that Turk has been designed when we try to do some of these experiments. So, but I think maybe the solution is that we should stop using Turk and build our own thing that actually does do. Well, yes, but as you've discovered, it's like tricky to get people to. I mean, it's funny. Like, the things that turn out to be difficult are not necessarily the things that you expect, right? So I think the single biggest problem that we have with running virtual lab experiments is just having a panel of people, Like, it's just getting the people. Recruitment is the biggest problem, right? Recruitment and retention is the biggest problem. And it turns out panel providers, they know this, right? People who do surveys like Pew Research, they spend a lot of time and a lot of money, or Nielsen or any of these people, they know how difficult it is to do this thing. But social scientists are sort of like la-di-da, like it's all about the theory, and I'll build my fancy interface, and of course the people will come, and then they don't come. So so it's a I mean, we were very lucky with Music Lab, which was sort of built on this field of dreams principle, right? We just sort of threw it out there and got tens of thousands of people, and that's great, but we've been unable to replicate that for over a decade now.
Well, viral events are very rare. So.
Also, the web has changed. I mean, it's actually probably more difficult to do Music Lab now than it was back in 2006. Sorry, the question.
I guess I have two questions, and I'm just going to ask both of them, and maybe you don't have to answer both of them.
Right.
The first is, in terms of the laboratory work, my bigger concern is actually about the motivation of the individuals. Right? So there's a long-running debate about whether chimpanzees or humans have better social memory, and a lot of it boils down to whether we think we can motivate humans to work as hard at the social memory tasks in the lab as we can the chimpanzees. And so in the case of the cooperators, there's no real penalty for defecting, aside from maybe people intrinsically wanting to win the game. And so do we actually think that those will translate out into the real world if there is a meaningful penalty? The second question is, in terms of the viral aspect, I mean, the theory from epidemics, and you know this, is that if we know the number of susceptible individuals, we know the contact network, we know the per contact probability of transmission, then we can tell you something about probability of a large outbreak, the final number of infected individuals. And I'm not convinced at all that we can't do exactly that same thing with the Twitter data, that it could be an effect of the network or the number of susceptible individuals. And it is interesting that the patterns don't look like what we think most human epidemics look like, although I'd argue we don't know what most human epidemics actually look like. But that doesn't necessarily mean that the underlying physics or the model are wrong. It just means that we need to understand what's different about the Twitter network than the human network.
Okay, so I think that was 3 questions, but they're all interesting questions. So the external validity problem, couldn't agree more. I think way too much scientific effort has been devoted to studying the prisoner's dilemma and public goods games, and surprisingly little has been learned from all of this effort about how to do anything in the world, right? For exactly this reason, that as soon as you go into a workplace or an Amtrak car or or the street, you've got a lot of other things going on that are not properly accounted for in your experimental design, and so it's very difficult to come up with any kind of policy recommendations from the observation that this happened in this experiment, right? So I think that for us the main point was really a proof of concept that you can run an experiment for a month, and B, you see new things, right? Now, I don't know that those things would help you any more than the other stuff that people have learned about from punishment and rewards and reputation and all these other sorts of things that people have studied in lab experiments. But it definitely was a qualitatively new finding, right? And I would like to be able to do more realistic experiments that also ran over similar periods of time. Okay? But completely agree that we would really love to do this, is sort of find ways to sort of experimentally study cooperation in the field, right? In an actual real environment. And I have a sad story about doing that, but it didn't work, and so that's why you don't know about it. But because of Turk. The second question about, well, you made a statement, sort of as if it was an obvious thing about how, if we just know the parameters of the population, we know how big the thing is going to get. We could not disagree more with that statement, right? That is not true. We can if we assume uniform mixing, right? we cannot if we have complicated network structure, which we do in the real world, right? So we actually have a paper from over a decade ago where we look at real SARS data and we look at childhood disease data from the Faroe Islands, and we show very straightforwardly that if you have critical individual level events like somebody hopping on a plane and taking, or a train, or going from Hong Kong to Toronto, that you have sort of unbounded error in the size of the epidemic. Okay, so that's point number one. So I don't think it's true that given the parameters of the model, you can predict very well at all, and people are lousy at predicting epidemic sizes. Terrible, right? Maybe if you knew the whole
epidemic models to the Twitter data and tried to do predictions.
Yeah, we've done that. So we have another paper. So that's your third question, and we have done that. And so there actually, the non-viralness of things kind of helps you, right? Because it really is dominated by how many followers the person who introduces the content has, right? Famous people get more retweets than nobodies, and that's about the best you can do, right? So it turns out that a very simple linear model with one feature, which is just what's the average number of retweets you've gotten in the past, gets about 40% of the variance, right? And it's almost impossible to do better than that. Right, so you give it thousands more features and it doesn't do any better. You do run topic models and classify the tweeter and do interaction terms between them and the content. None of it helps. So yes, you can do something, right? I don't know. Do you think R squared of 0.4 is good? Then it's good, right? It's better than nothing, right? So you can certainly predict things somewhat, right? Going back to the other question about, we could say, I think that is probably disappointing to most people. If you ask them, if you showed them a plot with, R squared of 0.4 and said, is this good? They would probably say, oh no, surely deep learning can do better than that. But I think there's good reasons to think that there are intrinsic limits to predictability, not just of human epidemics, but also things on Twitter. And maybe you may be able to do better on Twitter than almost anywhere. I actually think that that's probably true. Twitter is almost like the best case that you have for predicting things, because it's so simple. There's not a whole lot else going on. It's dominated by these hubs. Nothing's really spreading anyway. So if you can't do well there, then you probably can't do very well.
I would say as a social scientist, an R squared of 0.4 sounds magnificent.
Most things are like 0.2 or 0.05. IQ is like 0.05. Big 5 is like 0.05. Conscientiousness is 0.05. So yeah, but it's crazy though that people talk about as if that's predictive. We've understood, that grit is the key to success. It's like R squared of 0.04. So it's not actually. It's like what they should say is 95% of the variance is unexplained, right? Move along. So by those standards, 0.4 is, if you're a high frequency, hedge fund, 0.4 is amazing. You're doing there overnight, right? If you're doing online advertising and you're like showing billions of ads a day, 0.4 is great. So everything is sort of relative. So not just to the baseline, but also to the thing that you're trying to measure, right? And if what you care about is, averaging over billions of things and just doing better than the other person, then that could be fine, But if you are, if you're trying to decide whether to go to war or not, or invest all of your retirement savings in a single bet, then maybe 0.4 is not so good.
So I think that 0.4 not being so good is, I don't know if that's the optimal note to end on, but I think that this was a great talk, and I thank you, Duncan. So.